Are there any questions? No? Well, let's see. Let me talk about some of the steps here. This step where we separate out the iron, chromium, and aluminum, here you want to use excess sodium hydroxide. Because if you don't get much precipitate here, it's kind of hard to do the remaining analysis. So make sure you use excess. The hydrogen peroxide, yeah, we just keep an eye out for changing of this from the gray-green to the yellow solution here. Then we'll have this rust-colored precipitate. With this rust-colored precipitate, you use a minimum of HCl, just enough to dissolve it. It shouldn't take much to dissolve this. And then we're going to precipitate out this Prussian blue.
So minimum of HCl and maximum of sodium hydroxide, you said?
Well, an excess of sodium hydroxide. Make sure you get as much of the precipitate out as possible here. Also, we don't want any of these ions. Let's say if we didn't precipitate it out completely, some of these ions will go over here and screw up the results over in the next branch. And so you got to make sure you get rid of all these ions. However, well, this is for the. So we get rid of the iron, we get the aluminate ion, and the chromate. And then we're going to heat it to remove the hydrogen peroxide. We got to do that before adding the ammonia. So there should be no hydrogen peroxide. Now, if you add an excess of sodium hydroxide here, then that means you're going to have to add extra HCl here. Because we're going to neutralize the sodium hydroxide first before we can break up the complex. Okay, but the other reason for getting rid of the complex is the HCl is going to convert the chromate to dichromate, and then we convert it back down to yellow chromate with base, and we'll precipitate out the aluminum. Here you can use excess ammonia. There's no problem with using excess ammonia here. Precipitate out this. If we use excess ammonia, then we have to add a little extra HCl to neutralize that excess ammonia, and then dissolve this. And then we add the dye, and then precipitate it again with the red light. So I think I talked about that last time, as well as the barium chromate branch. Okay, the remaining cations should be calcium, magnesium, nickel, and zinc. All right, so for the remaining cations, these stay in solution. These are the +2s that we tried to avoid precipitating. This is the reason why you add ammonium here is to buffer the solution so the pH doesn't get too high. If the pH gets too high, then we'll start precipitating out the magnesium, nickel, and zinc as hydroxides, because these also form insoluble hydroxides. And so this is acting as a buffer here. Now, the first step here is we're going to precipitate out the calcium with oxalate. The magnesium, nickel, and zinc don't precipitate out with oxalate, just the calcium. And we form white calcium oxalate, so we want to maximize this precipitation here. Then separate, wash, and then we should end up with white calcium oxalate. This white calcium oxalate we can dissolve with HCl. This is just double replacement or reaction. We form calcium chloride and oxalic acid. And then we form aqueous calcium ions. Aqueous calcium ions, if that's all there is in solution plus oxalate, then what we're going to do is we're going to do a flame test. The flame test for calcium, it gives a very faint, what we call a brick red color. And this color doesn't last very long. It lasts for like a second or two. And so you have to be quick on your observation. Versus sodium, this color is very faint and difficult to detect. Sodium is very easy to detect because you barely need any sodium to see it. Since sodium is a common contaminant for our platinum wire here, we need to clean this. And a good indication is if it doesn't burn yellow. If it doesn't burn yellow, then it should be pretty clean. And so what you're going to do today is we only want to clean this once because cleaning this is such a pain. The way we're going to clean this is we're going to get some concentrated HCl. Don't get too much, as if you get too much, you're going to have hot glass coming into contact with liquid. When you have hot glass coming into contact with liquid, it's going to crack and it's going to break. And so what we want to do is we want to see how much HCl we can put in here without touching the glass. And so in my case, I'd probably put about this much to cover about 2/3 of the platinum wire here. And so I'm going to put the concentrated HCl here. The concentrated HCl gives off harsh fumes. And so we're going to do this in the hood. If you're cleaning this out in the open lab, then you're exposing yourself to other ions that might be on here. For the sodium flame test, there are other ions there. And so in the hood, working with the burners is a bit more difficult because there's a wind current there. And so you have to have a strong flame inside the burner. And so what we're going to do is we're going to try to dip this in concentrated HCl, burn it in the hood, dip, burn, until it comes out clean. Once it comes out clean, there's no evidence of yellow in the flame. Then you're ready to do the calcium test. When we do the calcium test, we'll dip our platinum wire in the test tube here, get some calcium solution, and then put it in the flame, and then quickly look. Do you see a faint red color? If you see a faint red color, that's positive for calcium. Okay.
Does that also need to be done under the hood?
This one does not need to necessarily be done in the hood.
Okay.
However, the sodium test should be done in the hood, because what you're going to do is after you test this, and you're going to test positive for this, hopefully. After you test positive for this, then you're going to get a little bit, you just need a tiny bit, a couple of drops or something of your original solution. So put a little bit of original solution in here, maybe 5 drops or something, and then dip it and then check it. Actually, you only really need 1 drop because sodium is so sensitive. Like if you have 1 drop of your original solution here, and your original solution does contain sodium, you're going to get a very intense yellow flame. And then if you had to clean it, you got to do it in the right sequence, because if you test positive for sodium, you're going to be cleaning it for a long time to test for calcium. So you have to do calcium first and then sodium second. And so this is a great place to insert the sodium test, which we skip. And the sodium test is you get a small sample of your original unknown, dip it, and then test it. But your original unknown also contains things like silver ion and other things you don't want to breathe. So do that in the hood. Now, calcium may be okay. It's not terribly hazardous. All right, so that's the test for calcium. The platinum wire, don't lose this because I think this is, how much is this? Maybe this is over 100, maybe $200 platinum or something. I forgot the cost. It's really expensive. And so go on over here. So we're going to evaporate to remove. So the ammonium, we're going to try to drive that off as ammonia vapor. It's going to come off as ammonia with sodium hydroxide. So get rid of that.
Do we heat it or just move it?
Yeah, heat it. You're going to heat it because that could interfere. Where will it interfere? Let's see. It doesn't look like it interfered. I have to look at the reactions again here. But anyway, what we're going to do is we're going to add the sodium hydroxide. The sodium hydroxide, we need to add excess. Excess sodium hydroxide will precipitate out to +2 magnesium hydroxide, nickel hydroxide, and zinc hydroxide. Zinc hydroxide is a white PPT. And so if you add just enough, then you'll get a white, green, and a white PPT. But what we have to do is we have to add excess hydroxide to form the tetrahydroxo zincate ion. These ones do not form tetrahydroxo complex. So we're safe there. And so just only the zinc. And so we got to make sure we dissolve all of the zinc to form this. And then we'll be left with a white-green precipitate. This white-green precipitate will add ammonia. Now, this is another thing. Here, magnesium does not form an amine complex, but nickel does. And so by adding the ammonia, we're going to complex nickel as a tetraamine nickel ion. and the magnesium will just stay as a precipitate. So how do you know this? You would look it up, in a table, what complexes form. And this is just strictly observational stuff right now, not theoretical. And so we can separate these because one forms amine, the other doesn't form an amine complex. And then magnesium hydroxide, we can dissolve in HCl, minimum of HCl. We got to wash it, of course. We do that with each of these. So we have a clean, pure, white magnesium hydroxide dissolved in a minimum of HCl, and then we're going to reprecipitate it out with a magnesium reagent. Magnesium reagent is a blue dye, and so it's going to color it. Now, what we're looking for is a blue precipitate. We're not looking for a blue liquid. The same thing over here. The red lake is not looking for a red liquid. We're looking for a red precipitate. That's the red lake. So the blue lake, we're going to get a blue precipitate. It's similar to the red lake, except it's just blue. And then we centrifuge this. When we centrifuge it, that jello settles to the bottom and creates a lake-like precipitate.
So we add magnesium, and then we also add.
That's not magnesium. This is called magnesium reagent.
Magnesium.
Yeah. If you add magnesium, you'll definitely test positive for magnesium. But the thing is this. Here's another tip. If you ever want to see what these look like, if you look at the dropper bottles there, in the dropper bottles, you'll see every single cation on our list. And so if you ever want to make a comparison, let's say, is that really the red lake or is this really the blue lake? Just grab the bottle of magnesium or grab the bottle of aluminum nitrate from the dropper bottle, add a few drops, add some hydroxide, see what it looks like, And then you can make a direct comparison, especially with color. Sometimes colors are tricky, but the colors might not even match that. So let's say you're interested in what barium chromate looks like. The color might not match exactly because if you have impurities in there, that could mess up the colors as well. So the magnesium reagent is this dye. It's going to be colorless until it complexes with magnesium. This complexes and then changes the color to blue. All right, with the amine complex of nickel, we're going to add dimethylglycine, and this is what it's going to do is it's going to knock the amines off and precipitate this as nickel DMG2. And this would be the formula for DMG, and this is a red precipitate here. Okay, then finally over here with the tetrahydroxyl zinc, okay, we're going to precipitate it with the hexacyanoferrate 2 complex ion. Now, in this particular one, this is called a mixed cation salt. So we'll need 3 zincs, 2 potassiums, and 2 of the complex anions. And this forms a gray-blue precipitate. It depends on how, the crystal structure and how it packs for these. But this zinc is going to prevent it. If it were just the potassium salt should be soluble. And so we get the gray-blue precipitate. Hopefully by the end you have enough to see, Just a tiny bit of precipitate is enough, because otherwise you wouldn't have gotten a precipitate at all. No precipitate at the end means you probably lost it on the way there. If you did lose it on the way there, and you want to see what it should have looked like, then you can grab a bottle off the shelf. It depends on how much time. If you start running out of time, then you might want to repeat. But, we might not, let's say this branch went out okay, you might just want to repeat it from this branch, let's say. And so to repeat it from this branch, I just grab some off the shelf, calcium, magnesium, nickel, and zinc. Mix it together, and then start from here, rather than go all the way back. That'll save you some time. Or let's say you mess up, if you mess up, you accidentally threw away the decantate you're not supposed to throw away, well, you can just mix up some decantate that should have been there if you start running out of time. But, the more times you do this, the easier it gets, for sure. Okay, are there any questions on this? So,
Oh, wait, yes.